Hey guys, Mr. Betts here. I want to take a look at a couple examples where we are given a definite integral and we want to rewrite it as a limit on a Riemann sum. We are not being asked to evaluate that limit. We're not being asked to evaluate the definite integral here. We just want to rewrite it as a limit. So let's just take this one step at a time here. With the first one, I'm going to go kind of slow. So first thing I want to do here is using the limits here, I want to figure out how wide each subinterval is going to be. In fact, let me do this. So this is going to be the limit as n approaches infinity. So n is going to be the number of rectangles we use. And then the right Riemann sum is, if you remember, it's going to be the sum from I, and sometimes you'll see I, sometimes you'll see K. Definitely don't want to use N because N is being used to represent something else. But this I here is going to be the number of the rectangle that we're on. So if we're adding, say, 10 rectangles together, I is going to count from 1, 2, 3, 4, 5 up to 10. Um, the height of each rectangle is going to be given by the function at some point, and I'm going to leave it at that right now. And then times the width of each rectangle, and the width of the rectangle is going to be delta x. Now we can figure out what delta x is. I was kind of getting to this earlier. We're going to use the limits here, b minus a over n. So each rectangle is going to have a width of 3 over n. So if we're using, say, 10 rectangles, the width of each rectangle is going to be 3/10. And those 10 rectangles are going to have a total width of 3, which is how wide the interval is. Now, I put the delta x out front. You'll often see the delta x over here. It really doesn't matter. Delta x does not depend on I, so it doesn't matter which rectangle we're on. Delta x is always the same. So essentially, we can factor it out from inside here to outside, and I think that just simplifies the algebra part of it. The x star that I have here, I want to draw a quick diagram of the x-axis. We're going from A to B, and using the right Riemann sum, the width of each rectangle, remember, is delta x. So the x coordinate that we're going to plug in the first time here is going to be a plus delta x, and then it's going to be a plus 2 delta x, and so on. So this is going to be in the form a plus I delta x. With I starting out at 1, the first one here is going to be a plus delta x. All right, so what I want to do now is take this expression and plug it into the function for x. So I'm going to replace the delta x with 3 over n. I'm going to plug the a, which, by the way, a is 1. So this ends up being 1 plus 3i over n. So we're going to plug that 1 plus 3i over n into the function here for x, and we get the limit as n approaches infinity of 3 over n, that's delta x, times the sum from I equals 1 to n of e to the 3 times 1 plus 3i over n plus 1. And obviously this exponent is an expression that we could simplify if we wanted to or we were asked to. I am not asking you to do that right now, so that's it. That limit right there, if we could evaluate it, is going to be exactly the same as the area given by this definite integral here. Now, I want to do this exact same example, except use a left Riemann sum. So to start with here, I'm going to start with looking at the x-axis and see what our left endpoints are going to look like. When we use the left endpoints, the first one is going to be a. The second one is going to be a plus delta x. Then we're going to have a plus 2 delta x, and so on, all the way up to the last one here is going to be a plus. Now, if the first one here we're not adding any delta x's and we're doing this n times, this is going to be n minus 1 times delta x. Okay, so the rest of this is going to be the same. So this right here these expressions are what I'm plugging in to the function to get the heights. I do want to point out that the first one we can think of as a plus 0 delta x. Then we have a plus 1 delta x, a plus 2 delta x. So essentially the number that we're multiplying by delta x, instead of going from 1 to n, is now going from 0 to n minus 1. So we can actually write our answer in the exact same form. Remember, delta x from the last one is going to be the same as this one. So we're going to have 3 over n for delta x times the sum from I equals 1. Sorry, I'm going to make that I equals 0 because I want to start at 0 times delta x. And we're going to go up to n minus 1 instead of n. And then in the function, I'm going to write this real quick, f of a plus I delta x. However, we're putting in for a, we're putting a 1. I is going to stay the same. Delta x is 3 over n. So 1 plus 3i over n is getting plugged into the function. So that's going to be e to the 3 times 1 plus 3i over n. Nope. Yep. Sorry. Plus 1. Okay, so this right here looks really similar to our answer here. The difference is just our sum here, instead of going from 1 to n, is going from 0 to n minus 1. Now, I will say that you'll see some multiple choice problems that ask you to use a left Riemann sum, but they're going to force you, with it being multiple choice, to start at 1 and go to n. So I want to look at that real quick before we wrap it up here. So we're going to go from 1 to n instead. So the idea here then is what we're plugging in for x, these things down here, we still need it to start at a plus 0 delta x. So what I'm going to plug in for x is going to be a, which is 1, plus, now to make the n into a 0, or I'm sorry, the I into a 0, since I is starting at 1, I'm just going to do I minus 1. So I minus 1 times delta x. And what that does is it takes the I value, it subtracts 1. So when we start at 1, it's going to add on 0 times delta x. And effectively, we get the same thing here. So this is what I'm plugging in for x here. So we get e to the 3 times 1 plus I minus 1 times delta x, which is 3 over n, and then plus 1. Okay, so this is a little bit messier, and algebraically we could simplify this a little bit to make it cleaner, but we don't need to do that. This is a perfectly legitimate answer here. I did mention, though, we might be forced into this with a multiple choice problem, and with it being multiple choice, there is a good chance that there is going to be some simplifying done there, so make sure that you're just able to match up the answer that you get with the correct answer among the choices.